Hello there. Hi, I'm Doug Picklyk, editor of HPAC Magazine, Canada's source for heating, plumbing, air conditioning, and refrigeration information and news. And this is 30 Mechanical Minutes, virtual content for real-time professionals. Once again, I'm very happy to be joined by a preeminent expert in the hydronics field and a regular contributor to HPAC Magazine, Mr. John Siegenthaler. Hi, John.
Good to be with you, Doug.
Nice to be here again today. We're going to be talking about circuit purging, getting the air out of your hydronic system. So from the initial fill of a newly installed system or refilling a circuit after servicing, how do we best get all of the air out? I'd also like to take this opportunity to thank our sponsor for today's 30 Mechanical Minutes, and that is Wolseley Canada, the national wholesaler serving the mechanical industry with over 220 branches from coast to coast. Thank you, Wolseley Canada, for your continued support. All right, John, we're going to start. I'm hoping you can just tell us briefly, why do we need to get all of the air out of our hydronic systems?
Yeah, sure. Well, hydronic systems ideally are meant to operate air-free. They're meant to operate with just water. There's a number of things that can be problems in any closed-loop hydronic system when air is present, depending on how much air is there. And it can range from corrosion due to oxygen coming in contact with ferrous metals. Even sound can be a problem. Inadequate flow rates, if there's a mixture of air bubbles and water, circulators don't create the flow rates that they're intended to. In some extreme cases, you can even have air binding in systems that would prevent any warm water from the heat source from reaching the heat emitter. So there's a range of problems that can occur. And fortunately today, the methods we're going to talk about, it's fairly easy to remove the air so that these problems don't occur.
Okay, so I know you've there's methods have changed over time. So hopefully you can talk to us a little bit about how these methods have changed. And I think we have a slide here.
Yeah.
Yes, tell us about this.
Well, here's a hydronic system, a graphic I took out of some old heating manual, probably dating back around early 1900s. And it's what we commonly refer to as a gravity system. You'll see the boilers down in the basement and there's sloping piping leading up to the heat emitters. And way up at the top, you'll see a tank with a pipe that actually goes outside. No circulator in a system like this. The flow is just created by the buoyancy of warm or hot water relative to cooler water. And these systems basically relied on air over time to just rise to high points where there would be vents, perhaps on the radiators, the high point of the radiator, or ultimately up into that tank up in the attic. And it was a slow process, a fairly inefficient process by today's standards. Eventually, most of these systems could reduce air content to a level where they function correctly, but again, our modern methods have significantly improved on these situations.
Okay, so there can be air pockets that form and also air bubbles in the system as well. And those are two different issues. Is that right?
Well, yeah, you can have air bubbles that will accumulate and form an air pocket. And if that pocket is large enough, especially with an old system like that without a circulator, portions of the system would become, I've heard the term airbound or airlocked, where just imagine several feet of vertical air in a pipe at a high point, and the water simply doesn't have the ability to move past that air. And without that, we don't get circulation, and without circulation, we don't get heat. So, here's some of the older hardware. And this is not to say that these devices aren't adequate, but just to give you a quick orientation, in that upper left, you'll see what's called a baseboard T. And it's a common fitting. You'll find this on many fin tube baseboard systems. And you'll see the arrow there pointing to that little port at the top of the T where there's a small little manually operated vent. And again, the idea was to put these at high points. In a typical baseboard system, the baseboard element itself is the high point. So each baseboard would have one of these with a manual vent. And I can actually remember running around with a coffee can, opening up these vents and just kind of waiting for the air and the water to come out. It worked, but again, relatively inefficient. Down below, you see an air scoop, that cast iron device. Basically, that was just creating a high point in the piping system. And the idea is that the bubbles would ride along the top of the pipe and they would accumulate in that upper chamber. There were some internal baffles that would help steer some of those bubbles. And then up at the very top, there's an air vent that would eventually, if you will, they burp the air out of the system. These devices are still around. You can still buy them. They work to an extent, but they don't work as efficiently as a modern, what we call microbubble air separator. And primarily the difference is microbubbles are very, very small. In fact, you cannot see them with your eye. They make the water look cloudy. And because they're so small, they're very easily entrained with the flow. So water containing microbubbles could often pass right through one of these air scoops with minimal displacement of the air. The air scoops really kind of counted on larger bubbles eventually forming from these microbubbles. So yes, they could get the air out of the system to an extent, but it would be a much longer process. And then over on the far right, again, these fittings are still out there. They're not as common today, but these were specialty fittings, in this case from Bell & Gossett, that were designed to capture air bubbles that were forming at the top of a boiler and actually route those air bubbles up to what's called a compression tank. You see the tank up over the top of the boiler. And so in a sense, again, this was I'll call it an early generation method of separating bubbles from liquid water and routing the bubbles, in this case, not necessarily ejecting them from the system. They would go up and they would basically stay as air in that compression tank. So again, these are earlier generation products. They function to a degree, but if we go to the next slide, we'll show you that things have changed. Today, right in the middle at the bottom, most systems today are being designed around a microbubble air separator. And you'll see it's a chamber. Typically, they're made out of brass, or in larger commercial sizes, they're made out of steel. But within that chamber, there's what's called a coalescing media. And what that coalescing media does is it allows the microbubbles to actually cling to surfaces and coalesce or come together into larger bubbles. And as those larger bubbles form, they rise upward, and up at the very top is a float type vent that will automatically eject those bubbles. So the big difference between the old air scoops and the modern microbubble air separators is really the ability of the microbubble separator to capture smaller bubbles, and as such, it's more efficient. It will help you de-aerate the system faster than what the air scoop would do. And typically these are placed at the high temperature locations in the system. You'll see it up above the boiler there. And the reason they're put into higher temperature locations, the gases that are in water, and I should go back to kind of a fundamental concept here. When you put cold water into a hydronic system, anywhere from about 3 to 4% of what you put in that system is actually not H2O. It's not water. It's dissolved molecules of oxygen, nitrogen, carbon dioxide that as molecules, you can't see them in the water. The water could appear perfectly clear, but as I said, they're not H2O molecules. And that's what we're trying to capture. That the oxygen, dissolved oxygen in particular, when we de-aerate the system properly, that oxygen content is of no concern. So back to the schematic, when the water is hottest, the ability for the water to contain these dissolved gases is minimal. So you can sort of think of hot water going through an air purger almost like squeezing a sponge. you're squeezing the air, the dissolved air out of the water, capturing it in one location and ejecting it from the system. And then on the left, you'll see a common valve that is used today. It's called a purging valve. In earlier days, these were done by taking a ball valve, putting a T in the pipe upstream of the ball valve, and then putting another ball valve on the side port of the T. And you could still do it that way, but the industry's responded with pre-built combinations of two ball valves and a hose connection, so that these can be installed at locations where we want to try to capture air coming out of the system. And in that schematic, you'll see the blue piping there. That's your automatic fill system. If we start with the assumption that that system is empty, just the piping and the bore are full of air, we're going to open the fast fill lever on our makeup water system. And you'll see it's just to the left of the purging valve. So the main handle on the purging valve, the inline ball valve, would be closed. That forces all the water flow going to the left. And what's driving that water flow is city water pressure. So we're going to get a good solid flow velocity established. And think of that water sort of like a piston in a cylinder. As the water rushes through the piping, it's pushing the air ahead of it around the circuit. And then eventually it comes back to the side port of the purging valve. That would be open and it would be connected to a hose. And typically that hose would run either to a bucket or to a drain. And when you fill up the system, when you open that makeup water, it might take, depending on the size of the pipe and how much pipe and volume you have, anywhere from maybe 15 to 30 seconds. You'll hear the air coming out the hose, and then you'll start to see water kind of spitting out the hose. And pretty soon you'll get a nice solid stream of water coming out the hose. And at that point, you've displaced most of what we call the bulk air in the system. And by bulk air, I mean the air that we can push out through this forced, what we call forced water purging. Remember, some of the air is still dissolved as molecules, and that's where the microbubble air separator, if you will, is kind of the cleanup. The
Right.
Forced water purging might remove 95+% of the air, but the cleanup, the dissolved air removal, that's the function of that microbubble air separator.
And this, again, the forced water, you just kind of blow this up.
Very simple system there. It's a single loop. You're just basically blasting the water around. And I put a note down at the bottom. To be effective at entraining air, water needs to be moving at least 2 feet per second. That's especially important in a pipe that is a vertical pipe where the flow is going downward. Because remember, bubbles want to rise. And you can actually calculate how fast bubbles will rise depending on their size. But 2 feet per second going down is fast enough that the water can entrain or grab that air and actually push it or pull it along and push it towards the side port of the purging valve.
Okay, so this is like a single circuit.
Right.
So how do we change things or adjust things for multi-zone or even primary and secondary circuits?
Sure. Well, you'll see on this next graphic here, we've got 4 zone circulators, and they have isolation flanges on them. So we could purge one of those at a time. And then down at the bottom on the lower header, you'll see there's a purging valve on the return side of each individual zone circuit. So basically what we're going to do, Doug, is we're going to repeat what we did for a single circuit. We're just going to repeat it 4 times. We're going to start with one zone, close the other zones off, force all the purging flow from our makeup water system to go through that first circuit, pushing the air out ahead of it and out the side port of the valve. And once we have a clean stream coming out, we're going to basically just move to the next circuit, shut off the first circuit, and repeat the process. So depending on how many zones you have, this only takes a few minutes in most cases, especially if we have good water pressure on our plumbing system.
Okay.
So it's good practice to have a purging valve near where each individual zone circuit combines to the return header. And the other nice thing about it, if you ever had to isolate one of these circuits, let's say somebody accidentally drives a drywall screw through a pipe. We've got a valve on the return side of the circuit. We've also got valves on the isolation flanges on the circulator. So we can close both sides of the circuit, isolate it without taking the other circuits out of operation and do the repair.
Okay. Is there, you make a note down here, the expansion tank location.
Yeah, it's oftentimes you'll see the expansion tank tied to the bottom of the air separator, which is fine. But when we have a what we call a low flow resistance boiler, and a cast iron boiler is a good example of it, it is fine to put the makeup water system, including the expansion tank, as it's shown in this schematic. Now, the reason I say it's fine with a low flow resistance boiler, if we put a high flow resistance device in there, let's say a ModCon boiler with a coil type heat exchanger. Remember another principle, we've talked about this in past sessions. We want to be pumping away from where the expansion tank taps into the system. And it's not so much a distance factor as it is the pressure drop between where the expansion tank is and where the inlet of the circulator is. Even though we might have a few feet of piping in this schematic, the majority of the pressure drop is going to be out in those individual zone circuits. So tapping that expansion tank in like that is fine. One of the benefits of doing it this way is the expansion tank actually stays cooler. The shell of the tank stays cooler because it's near the return side of the system. And the less we heat the shell of the tank, the less pressure buildup we get just due to heating. So it actually lets the pressure fluctuation in the tank be more determined by just how the water in the system is heating up and cooling down, as opposed to conduction of heat from the hot side. If we tap it right into the bottom of the air separator, there's going to be some conduction of heat warming the shell of the tank. So it's actually a fairly common detail in Europe to see the expansion tanks mounted like this.
Okay, so this is the multi-zone, and then we also have the primary, secondary, same idea.
Right. Yep, in a primary secondary system, you'll see I've got a purge valve shown on the return side of each secondary circuit. There are some folks that instead of doing that detail, they'll put a ball valve between the two T's where it says closely spaced T's. I'll spread the T's apart, put a ball valve in there. That's okay, but keep in mind that once that secondary circuit is purged, the functionality of that ball valve, you're done. There's really nothing else it's going to do for you. Plus, it does add pressure drop between the two T's. And the concept of closely spaced T's is to get the pressure drop between the T's as close to zero as possible. So putting in a ball valve in between, especially if it's a standard port rather than a full port ball valve, it just, it works against this concept of hydraulic separation. My preference would be to put the purging valve on the return side of the circuit. Now, when you're done purging, you don't have that pressure drop between the T's, and you can isolate both sides of each secondary circuit if you need to do repairs. And the process of purging a primary secondary system, typically we purge the primary loop first, just get as much air out of the primary loop as we can. And then we would work from one secondary circuit to the next, just moving the hose, or, you could have multiple hoses involved. And, that way we can get the vast majority of the bulk air out of the system. You'll see right above the boiler, there's a micro bubble air separator. That's the cleanup. That's going to get the dissolved gases out of the system as the water heats up. Okay.
Now, I know you made a note about systems with glycol and how that might change.
Right. Many systems today, or subsystems, for example, we were talking earlier about, let's say, a snow melting subsystem that is tied to the main system using a heat exchanger. When we're going to put a mixture of antifreeze and water, first thing, we don't want to have automatic makeup on that system. And the reason is if there's a slow leak over time, especially if it's undetected, every time the glycol solution would leak out, it would be replaced with water. And over time, that just dilutes the antifreeze, and potentially that could lead to a freeze up. So no makeup water. So then the question becomes, well, how do I get the glycol solution into the system? And that's where one of these double ported purging valves is nice. And again, this is a residential light commercial application, but the concept does scale up to larger hardware. Essentially, what we're going to do, and you see it in the upper right there, we're going to have a container that will have our mixed antifreeze solution. So the antifreeze in the water, whatever percentage of antifreeze we're working with, that's already been mixed, and we're ready to put it into the system. So we're going to close the main handle on the dual port purging valve. That's the big handle there. We're going to close that, and what that does is it prevents the flow from passing from one hose to the other. It basically puts a block, a complete stoppage between those two side ports. Then we're going to use a small submersible pump, and we're going to pump the fluid from our container. If you look at the photo on the left, we'd be pumping it in. Let's say we're going from lower right to upper left. We'd be pumping it in on the gray hose. That smaller knob would be open. Actually, both of the smaller knobs would be open now, and the larger handle would be closed. So we're pumping it in. It's going to go around the circuit, just like it would if it was water. And it's going to come all the way back to the other port on the purging valve. It's going to come out the green hose and go back into our container. And again, we would just keep the submersible pump running until we have a nice, clean, no visible air returning through the outlet hose into that container. And a quick note, and I learned this lesson the hard way, make sure you fasten that return hose into that container somehow, because with a strong pump, that hose can take off sort of like a deranged elephant's trunk, okay? And it can spray antifreeze all over the place in a matter of seconds. So make sure you fasten that hose into that container. And, again, similar detail on if it was a snow melt circuit, if it was maybe a garage floor heating circuit that's going to have antifreeze in it, we'd put one of these dual ported purging valves in. And a large commercial system, you would probably build an equivalent assembly with a full port ball valve and then a T on each side of it, and a couple smaller ball valves for the inlet and the outlet. But again, the residential light commercial systems, this detail is so common that, and of course, using a pre-built valve like this is less expensive than field assembling the equivalent of it. So.
Okay. Now, you also mentioned micro bubbles and in circulators, which can cause some issues.
A couple other details, and again, these kind of come from some field experiences that I've had, as well as some others that have communicated with me. Many of the small zone circulators today, from just about any of the manufacturers, they come with a small check valve insert, and you see it right there, Doug circling it, and that's a spring-loaded check valve. When you install the circulator vertically like this, there is a potential for air to accumulate under that check valve. And because that check valve is literally within a couple centimeters of the impeller, that air will tend to displace water or antifreeze in the vicinity of the impeller. So when that pump starts up, there's actually a mixture of air bubbles and water in the volute around the impeller. And the impeller simply can't, if you will, it can't get a grip on that fluid and push that air through that check valve. Remember, these circulators, the impellers are designed to pump an incompressible fluid, and that's water or a mixture of water and antifreeze. So when we put air in there, we have a compressible mixture, and centrifugal pumps are not good pumping a mixture of air and water. So how do you avoid this? First of all, you do a really good job with your forced water purging. You try to get as much of that bulk air out of the system as possible. The other couple things you can do, one is you could pull that little check mechanism right out of the circulator. They're little plastic inserts, and basically in needle nose pliers, you can pull it right out. And you could install a check valve perhaps a foot or a couple feet above the circulator, so the air is not going to accumulate within the volute of the circulator. Or you can install the circulator with horizontal flow or even downward flow. And that orientation change eliminates the potential for those air bubbles to accumulate. So again, I'm not saying always install the circulator so you don't have this orientation, but if you do, make sure you do a good job of forced water purging. And if for some reason you can't figure out why a zone isn't pumping, this could potentially be the reason for that. And over on the far right, I put this in just to describe something that I'm sure every installer listening has experienced. When you first start up a circulator, especially with cold water in the system, you might hear churning sounds coming out of the circulator. You can literally hear that there is a mixture of air and water in the circulator. And what happens in a circulator when you have these dissolved gases in cold water? Remember, we said 3 to 4% of that initial cold fill water is actually dissolved gas. At the eye of the impeller, we get low pressure. And if you think about taking a can of soda or a bottle of beer and popping the top, and you immediately see bubbles forming. And that's what's happening. The low pressure at the eye of the impeller is causing these dissolved gases to form into microbubbles. And we get something called gaseous cavitation. And I put up at the top there, not vapor cavitation. And I just want to briefly describe the difference. Gaseous cavitation will be eliminated by forced water purging. You basically are going to blow that air out of there. The microbubble air separator will do the cleanup. Gaseous cavitation is going to go away. Vapor cavitation can occur in pure water, no dissolved gases. That's where you're actually causing the water to change from a liquid to a vapor. And that can be very damaging over time. Vapor cavitation will create sounds that sounds sort of like, I guess I'd say bacon in a frying pan. You get these snapping sounds. And without going into great detail, the water under vaporous cavitation will actually erode even a stainless steel impeller over time. So vapor cavitation is avoided by proper pressurization of the system. Gaseous cavitation is really a startup phenomena. So good forced water purging and a good microbubble air separator eliminates gaseous cavitation.
Okay. John, we have almost reached 30 minutes. Hard to believe it's gone by so quick. We do have a number of questions here, so I'm going to just jump right in and start asking a few of these questions.
Sure.
Carl asks, I've noticed that using an electric hot water heater tank is mentioned a lot only in Canada. I'm at the point of purging a small radiant floor with an electric hot water tank heater. Are there any special considerations for purging a closed system of this kind?
Again, I would put a microbubble air separator in at the outlet of the water heater. I would put the purging valve in, try to get as much of the bulk air out. But fundamentally, you've got a vessel rather than a boiler. You've got a vessel with more water volume in it than a typical boiler would have. So you're going to have more air in the system to begin with. Again, a purging valve and good forced water purging, you've got to fill the tank and get that water out into the piping. And then I would definitely put a microbubble air separator in to get the dissolved gases. But fundamentally, know that it's the same approach as you'd use with a boiler.
Okay. Mike asks, and I think this one came early, so it might have been when we were showing the micro bubbler strainer, because he asked, does this device have issues with dirt requiring an inline strainer, or is this equipped with that same thing?
Yeah, that's a good question. Actually, an air separator with a coalescing media in it will actually separate some dirt in the system. And at the bottom of the air separator, there's always a drain port. So one option that you have is to just take a boiler drain valve and screw that up into the bottom of that air separator. And then maybe once a year, just open that valve up. And if you do have some dirt accumulated in the bottom of the bowl of the air separator, that should flush it down. And you may know too that many of the companies that make air separators also make combined air and dirt separators. And fundamentally, it's an air separator at the top and it's a dirt separator at the bottom. So they extend the vertical chamber of the device. It simply gives the bottom of the device more space, more volume to hold more dirt. But the dirt coming back from the system, once it impinges on that coalescing media, will tend to fall and accumulate down at the bottom. So yeah, you could put a valve on the bottom of a micro bubble air separator, and on your annual maintenance, just open it up quick, flush out any sediment that's in there, and close the valve. It's fine.
I think it's the same person asking, is the preference to have the air separator device before the pump if you have a push-through boiler versus a draw-through boiler? Because not generally an issue, but often on a primary secondary, you would have the air device on the primary, not on the boiler secondary.
I follow it now. Yeah. If you're dealing with a boiler that is set up on a secondary circuit, I don't have any research one way or the other, but I guess I'd look at it. My preference would probably be to put the air separator on the primary circuit, simply because now it has all the fluid going through it. The argument about putting it into the boiler secondary circuit would be that's slightly hotter. So I think you could do either one. I have not done any testing, and nor have I seen any results of testing that would definitely point towards always putting it on the boiler secondary circuit or always pointing it onto the primary circuit. So I think either one would be adequate.
Okay. Dan actually asked the same question. Would an air separator be okay to be installed on the supply pipe of the secondary loop in a primary secondary setup? Or
Yes.
would you recommend keep it on the boiler supply of the primary loop, or maybe both locations?
Well, if you sell air separators, probably both locations would be good. I'm sure many manufacturers would love that. Keep in mind today, these air separators are available with a lot of different geometries. They're set up so they can go in horizontal pipes or vertical pipes. Some of the ones that are designed to go in vertical pipes will fit under a boiler, a wall-hung boiler, very, very nicely. So that's a nice geometric, arrangement of components. But again, I honestly don't know which fundamentally would be better. I think either one would be functional. Either one would definitely be better than an air scoop in terms of micro bubble collection. One thing you might look at from a cost standpoint, it might be slightly less expensive to put it in the boiler secondary circuit, assuming that pipe size is a little smaller than what the primary pipe size is. But I've seen it both ways, and I've seen it work in both ways. So I don't really have a strong preference.
Okay. Someone asks, are there any circumstances where an air vent on top of an air separator within a boiler room can replace the need for auto air vents at high points throughout the hydronic piping system?
Yeah, great
outside of the
question.
boiler room.
Yep, I would say yes. And what they're talking about, imagine a baseboard system where we have half a dozen baseboards and they're all high points in the circuit. So the classic approach would be to put some type of an air venting device on each one of those, either a manual vent or in some cases a float type automatic air vent. My experience has been today, we don't need to do that. With forced water purging, we can get the majority of that bulk air out, and the microbubble air separators really, when I look back in the hydronics market over the last 40 years, what are some of the key changes? And I can remember early on in hydronics, getting air out used to be kind of a worrisome thing. It was kind of cross your fingers and hope for the best. Well, when the microbubble air separators came into the market, that really did change the efficiency of getting that air out. And my experience has been it's not necessary to have all these high point air vents. With proper purging, a good forced water purging followed by the cleanup, as I've called it, with a microbubble air separator, I have not experienced any need to have those high point air vents.
Okay. Robin here says often it's most efficient to combine microbubble resorbers with a magnetic dirt separator.
Mm-hmm.
The problem occurs when the heat source has an integrated circulator. If you had to choose where to place the combined device, would you place it on the cooler return water to enable the dirt separator to protect the circulator?
He has identified a quandary, and I understand it. When you combine, let me back up. The ideal place for the air separator would be on the leaving side of the boiler.
Right.
The ideal place for the dirt separator, especially if there's an integrated circulator in the boiler, would be ahead of the boiler.
Right.
So if we put those two devices together, where should it go? Supply side or return side? Honestly, I don't know of any study that's actually identified it. I would probably default on the air side, going to the hot outlet side, because the magnetic portion is going to grab that material. If you're doing a good forced water purging, you should get most of the grit, I'll call it, out of the system with the forced water purging. So the amount of, especially a magnetite, which is very fine iron oxide particles, you're going to have some of that left. And quite honestly, I think most pumps would handle some of that. And, if you're really concerned about it, I would tell you the ideal is to use two separating devices rather than a combined device. If you've got a circulator or a boiler or anything, a BTU meter is another example. Any kind of instrument or device that really has a low tolerance for dirt, my design option would be put a magnetic dirt separator upstream of all those components, and then put the air separator downstream of the heat source. That is the better option. The combined air dirt separators, again, they do function, but it is a case where we are putting two functions together in one device to save money and to save installation time. And in doing so, there is a slight compromise over having two separate devices and being able to place those two separate devices exactly where we want them.
Okay. This person mentions the problem is there are no vertical dirt separators on the market, but there are combined vertical devices.
Actually, I believe there are some dirt separators that can be in smaller systems, residential systems, that can be configured into vertical piping. Basically, they take the flow and they route it horizontally, then they route it through the chamber where the magnet is, and then put it back into the vertical pipe. That configuration, though, I'm trying to think, possibly up to maybe 1.5 inch, maybe 2-inch pipe size, right, at the most. I'd have to check from a manufacturer, but when you get up into commercial systems with 4, 5, 6-inch diameter piping, I don't know of anybody that makes a vertical separator, a vertical geometry separator for that configuration. Okay, I'm going to ask 2 more quick ones here. Is there a certain PSI that is associated with 2 feet per second? No, it's not a pressure function. It's 2 feet per second. There is a flow rate associated with it. For example, in a 3/4 inch copper tube, just because it's used a lot in residential, I remember it's about 3.2 gallons per minute. So in round numbers, 3 gallons a minute is about equal to 2 feet per second in a 3/4 inch pipe. And you can look that up for different pipe sizes. But the bottom line is, with building water pressure 40, 50, 60, maybe even up to 80 PSI, typically achieving that 2 feet per second is not a problem when you're doing forced water purging. In many cases, you're going to be well above 2 feet per second. Now, the flip side of that would be if, let's say I'm trying to purge a system that has maybe a 3-inch pipe, and I'm using a tiny little submersible pump in a 5-gallon pail and trying to pump antifreeze in there. I'm just not going to, that little circulator or sump pump rather, is just not going to have the ability to get that 3-inch pipe or 4-inch pipe up to 2 feet per second. We're going to need a higher flow rate. So I guess the way I would leave that question is look at the biggest pipe size that you've got, figure out what gallon per minute would be equivalent to 2 feet per second. And then however you're going to add that fluid, either with city water pressure or with a sump pump, make sure you can get a flow rate at least that high in gallons per minute.
Okay, John, here's going to be our final question for today. In a system with long vertical risers, is it possible or faster to initially fill the system from the top, or is it always better to fill it from the bottom up? Thank you.
Again, I can't cite any studies that have compared those. I think probably filling it from the bottom up would win. And the reason I say that, air wants to rise relative to water. So air isn't looking to get pushed down and out through a valve. It can be with enough flow velocity, but just looking at it from a buoyancy standpoint, air wants to rise, as we talked about actually in that very first slide with that old system. So given the choice, I'd probably opt to fill it from the bottom up. Okay,
John. Well, thank you again for participating in today's 30 Mechanical Minutes webinar. And I'd like to also thank our sponsor once again, Wolseley Canada. For contractors across Canada, be sure to check out wolseleyexpress.com. And of course, thank you to everyone who joined us today on this webinar. Someone had asked, and yes, a recording of this session will be available on our website, hpacmag.com, in the days ahead. And you can see past episodes of 30 Mechanical Minutes found under the Tech Pulse section of our website and on our YouTube channel. I would encourage you to subscribe today. Well, I think that's it. Until next time, thank you so much for joining us, and I hope to see everyone at our next 30 Mechanical Minutes coming up before you know it.
Sounds good. Thank you, Doug. And
That's good. Thanks, John. Thank you, everyone.